This is Advent of Code 2020, day 24. The puzzle is called Lobby Layout. The crab has done a good job of navigating us to our resort, and so we are heading into the lobby, and we realize that they're doing a bit of renovating and retiling the floor. And we don't want to wait for them to retile the floor by themselves, so we're going to help out a bit. The tile they're using are hexagonal tiles, and so it's going to be arranged as hexagonal grid. And so we want to help them figure out, based on a set of instructions, which tiles need to be flipped on the white side and which tiles need to be flipped on their black side, because each tile has a white and a black side. So the instructions for which tiles need to be flipped which side are encoded as such. So an instruction like this says, from some kind of starting tile, maybe the entrance to the room, if we move to the east, and then we move to the southeast, and then we move to the west, then the tile that we arrive at should be flipped from whatever it is right now. So they're all going to start as white, and so then if we were to arrive here, we would want to then flip that tile over from white to black. This other example, we move north, then we move north, whoops, no, I'm getting the directions messed up. There's no north because of the way the tiles are arranged. There's just northwest, northeast, southwest, southeast, and then we can go east and west. So we would first go northwest, then we go west, then we go southwest, and then we go east twice, which would actually bring us kind of in a circle back to the tile that we started on, which is why we would then flip that tile over from white to black or black to white, depending on what it was at that point. So part of the challenge of this puzzle, you can see, just came out in me trying to parse this apart. We're given these strings of directions, and we have to be able to tease out whether the different directions, which of these 6 different directions we need to be going. And if I didn't say it already, the reason we have 6 of these is because they're hexagonal tiles, and because of the way the tiles are arranged, these are kind of the directions you can move to place a tile, on any given side of a given tile. So let's see. If we have a big set of instructions like this, there's 20 of them. That means it's giving us directions of 20 tiles that need to be flipped. So we would start here, we'd move southeast, southeast, so on and so forth. We'd eventually arrive at some destination tile, and it's once we arrive at that tile that we've identified it, and then we would flip it from the position that it's currently in, or from the side that it's currently showing. So in this case, 10 of those instructions would have us flip tiles once, so from white to black. And then another 10 of those tiles would have us flip 5 tiles over to black and then flip them over again to white. So that's kind of a nice sample that we can work with, and there'll also be a puzzle input. And so then the final result is we want to know how many of our tiles are left with the black side up. So I guess then the answer to this one would be 10 tiles, because all of them start as white, 5 of them got flipped to black and then back over to white, so it's just these 10 that remain black. So with all of that in mind, I'm kind of thinking it might be helpful to reference this blog here by Red Blob Games. I've read this before about hexagonal grids. It's a really awesome in-depth piece that talks about kind of some game design type thinking, and if you scroll past here, there's some geometry. It's all fun reading, but what I find interesting is their bit on coordinate systems, and I think this might help us out, because you can imagine one of these hexagonal pieces here being our west, east, northeast, northwest, southwest, southeast. So a tile like this is sort of conceptually what we need to represent in our program to solve this puzzle. And what's nice is we can actually work with a XY grid coordinate system in order to sort of keep track of where we are as we follow a set of these placement instructions. So you can imagine if we get southeast, then we would, I guess, add 1 to the y coordinate. If we got another southeast, then we'd end up in 1, 2. Am I altering it by moving along here? I think this is telling me how far away. Yeah, so 0, 0. So as we move east, we increment the x coordinate, and as we move sort of downward, we increment the y coordinate. But yeah, I guess where it gets a little bit tricky is that as we're moving, that first southeast has us just increment the y, but then we move another southeast, and now they both get incremented? Huh. That's interesting. And then, yeah, so always this first southeast from any of these is going to increment the y. And if we were to move southwest, we would decrement the x and increment the y. Yeah, that seems to be happening for all of these. Huh. So I'm trying to sort of reason through the logic of how these increment here, and I think if we can kind of get around to a set of rules that we feel good about, then we can use that as part of our system for tracking where we, what tiles on the grid are getting flipped over. Because I'm thinking if we can do that, then we can translate the set of instructions to sort of a single coordinate position, and then we can just store whether that coordinate position is black or not, and then at the end we can just add them all up. So yeah, what are the difference between these ones? Odd R horizontal layout shows odd rows right. Yeah, so I guess these are sort of some different schemes for doing this. Well, I wonder if this scheme makes any more sense. Oh, but this now shifts us to having north and south movement, so I don't think we want to deal with either of these. On the right, I think we want to stick with one of these left two. So any sort of south movement brings us into a grid where a portion of the grid where all of the y's are one more. So I think we start out at, if we start out at 0, 0, any sort of southerly movement would increase our y, increase our y, increase our y. A northward movement would then decrease the y, decrease the y. So, okay, that logic makes sense. So then how do the x's work? Start at 0, 0. Any sort of east movement would increment the x. Any sort of west movement would decrement the x. And then how do so a southeast movement would only affect the y here. But then a second southeast movement would bring us into this, I see, would bring us into this sort of new part of the plane. Huh. Oh, that's so interesting. So then how do we take advantage of that in sort of reasoning about our positioning? There's also cube coordinates. I think that might be, is that more work than it's worth? I don't know, you move to the southwest. You do -1 +1 to the, oh, this might be a little bit better. So we've got X, Y, Z. So if you move along one of the, if you move in one of the Z positions, that, or the Y positions, then the each direction on the cube grid corresponds to a line on the hex grid. Try highlighting a hex with Z at 0, 1, 2, 3 to see how these are related with Z at 0, 1, 2, 3. Z of 0, Z of 1, 2, 3. Okay, so moving to the west or the east leaves the Z intact, and then moving to the northwest leaves the Y intact, and then moving to the, moving to the northwest keeps the X intact, moving to the northeast keeps the Y intact. Oh, I see what they're telling us now. So this leaves the Y intact, but it decreases X and increases Z. Go in this direction, decrease. Oh yeah, so we can encode these rules then. So then if we just keep track of the X, Y, Z, then we'll have a unique coordinate for any given tile position that we end up at. Flat, pointy. Wow, that's really slick. Okay, so yeah, I'll have to reference this again once we start going, but I think this is really going to help with the solution here. So let's start with these, and we'll pop open sample txt. All right, and then we'll open up cart1.ruby, and we're going to have to read in this sample file, just like that. Okay, and we'll want to get, I guess, directions is what we'll call each of these lines. So we'll split them on new lines like that. So that'll be a series of directions. And so then for each of the directions, we'll have to follow it to a position, flip that tile. If that tile is known, reverse it if it isn't known, it's white, flip it to black. This rule's here because everything starts as white, and I'm imagining we're going to keep track of the tile positions that we encounter in a tiles hash, I guess. And at the end, we'll grab tiles.values filter where the tile side is black. And we'll just get a count of that, and that's what we'll put out. So that'll be the answer. It's how many of these come out as black. Unused argument tile side. Oh, oops, that's an assignment instead of a comparison. Okay. Great, so I think that's the skeleton of this program. The pieces that we need to still fill in are what does each directional movement correspond to in terms of updating the X, Y, and Z. X, Y, oops. Yeah. And then the other piece is, I guess, parsing apart each of the directions. So direction match, and what do we want it to match on? We want to pull off one at a time the thing from the front. So say the front of the string, and we want to either find, let's see, southwest, northwest, northeast, southwest, southeast, east, west. So something like that. So if the string starts with any of these 2-bit pieces, we'll match that, and maybe we can even call this thing direction. These are the directions. Running out of variable naming ideas here. What if we call these instructions? Like that. And then this can be a direction as a named capture value. So we'll do that. We'll get the direction match. So instruction. Instructions left to follow. Get the instruction, I guess. And so then while instructions left to follow dot is not equal to an empty string, then we're just gonna keep doing this stuff, I guess. So I'm imagining we're gonna loop through a bunch of times, sort of trimming the front of one of these direction strings until we have followed it to its end, updating the tile position each time, and then ultimately updating our tiles. So yeah, let's see. Tracking position gets, I guess, 0, 0, 0. And then, actually kind of like, about position gets struct.new xy z, like this. So then we'll say position.new 0, 0. And I think, yeah, let me just try that out here as well. So we'll create a position. Okay, we'll say P1 gets position.new. It's 0, 0, 0. Okay, P1.x, awesome. P1.x gets 1. Okay, so that'll work. We can just kind of go through, keep track of position, update it as we go. Eventually we'll say P1.2h, and we can use that as a key in the tiles hash. Yeah, I like the feel of that. Okay, so we've got our tracking position. We'll match on a direction. And so then case direction match dot direction when, so I guess here is where we have northwest, northeast, southwest, southeast, west, east. Oops. I'll change those to single strings so that Rubocop stops yelling at me. And yeah, here's where we're gonna fill in these details in this when. So each time we hit one of these whens, we'll do a different thing to the tracking position, and then we'll just keep looping. And in order to eventually hit an end case where this string is empty, we'll have to update instructions left to follow. So in order to do that, I'm going to say instructions left to follow gets direction match dot post match. Because I think what we'll get here is, you can imagine we get a string that's like southwest, east, north. Oh yeah, we already pasted an example. So if we have a string like this, we'll find this part first. And so then this east all the way to the end will be what gets associated with post match. And so that is how if we update instructions left to follow, we'll get everything except for the instruction we just followed. So that's the reasoning there. Okay. So I think we've got all of that in place. Now we just need to deal with these directional pieces. So let's revisit this. So if we move to the east, then we increase our x and we decrease our y. Okay. I say tracking position x gets plus equals 1. Minus equals 1. Okay. Did I get that right? Plus 1 to x, minus 1 to y. If we move west, then we do the opposite. So let's go ahead and copy these over here. And we'll make those like that. So again, the z is staying intact for these east and west movements. Now if we're moving north, east, or southwest, then the y is staying fixed. So northeast, we get a plus 1x minus 1z for northeast. Update the z like that. Okay. And then if it was northeast, southwest, I believe is going to be the opposite. So we'll make that a minus, and we'll make that a plus. And let's see, yeah. Minus 1 to the x plus 1 to the z. Okay. And so then lastly, we're moving along this coordinate system. The x stays fixed, and it's the y and z that change. So northwest gets plus 1 to the y. Northwest is plus 1 to the y. And minus 1 to the z. So that would make southeast minus 1 and plus 1. Okay, so that's our coordinate tracking there. And then ultimately, we come out the other end of this while, and we have to update the tiles hash with our results. So we come out the other side of this while end, and we say tiles tracking position to h. That's going to be our key. Gets tiles, and so we either got to look it up, and if it's not there, yeah, let's see. So current side up is going to be what we get from here. Oops. Paste that. And so if the current side up is, or it should default to white. Okay, now this is making sense. So if current side up equals white, then we get black. Otherwise we get white. So that's how we'll update those as we go. And this end is the each there. So then we'll come out the other end of the tiles, and that'll be our answer. Okay. What's this complaining about? Block has too many lines. That's fine. Let's try it out on a sample and see how we do. Struct. I sure did. Little typo. Now let's give that another run. Did you uninitialize constant position? Position. Okay. Great. Okay. And another time. Undefined method direction for... Oh, we're ending up with a positional match instead of the named match. Why is that? Got a capture group here. Huh. I don't know why that is. I mean, it seemed like it pulled the right value out, but it should be a named capture. That's odd. Well, what if we do that then? It's not finding anything. It's just stuck in, I think, that while loop. Okay, well, let's grab this. Up here, Yeah, up here. And I'm kind of curious to see, or yeah, we'll leave that commented out. So I'm curious to see if I pry into here, if I can make sense of what's happening with this bit of a match here. So let's grab our string. This will be, we call it instruction. Okay, and so then instruction.match. Assign that, so then match 1, okay, and then what's matched up? Post match. Yeah, that seems right. Still not sure why this isn't getting assigned to direction as a named capture. Yeah, that's rather strange. Huh. I wonder if there's a different way to do this, like that maybe. Oh, it doesn't like that at all. Okay. Is there something wrong with the keyword direction? Thought I had a pretty solid understanding of how these named captures are working, but not seeming to get what I'm expecting. Let's see. Ruby named capture. Oh. Because I put the, there we go. Whoops. Okay. So I put the question mark in the wrong spot. It goes there. So then I'm able to pull out direction here. And hopefully we're updating things down here. Direction match, post match. Eventually it should get whittled down to an empty string. Let's see. I'm gonna hit my pry. Oops. Oh, it wants us to do a hash access rather than a method. So we'll pull it off as a symbol. And we're stuck again. Okay. So it's not whittling that string down to be something empty. I wonder why that is. Curious to pry in here. And why did it stop me there? Instructions left to follow. Instruction. Yeah, so it seems like we've already trimmed it down. Oh, it's not getting... Oh. Whoops. We need to be matching on instructions left to follow, not instructions. Because that's the thing that's getting updated each time. And there's our answer 10. Awesome. Okay, so let's jump back over here. Let's grab our puzzle input. Let's copy it all over. And we'll create input.txt, paste it in here. All 581 lines. Jump back over to part 1, update what file we're reading in. Give that a save and see 523. That's a lot of tiles. Okay. And is that our answer? It is. All right, we got our gold star. That was part 1. In the next video, we'll look at part 2. Thanks for watching.